Okay, welcome everyone and people on Zoom and those who will see this in the recording form later. This is the TAM seminar and also Fluids at NU seminar. So let me tell you what Fluids at NU is. It is basically a community of fluid researchers at Northwestern, which is spread out across many departments here. So with the initiative from Dino Gino, Petia Rahosta and myself, we have put together this community in the form of a website where we can interact. So this is second of the internal talks within this series, so we can know about each other's work. So welcome Daniel. He is quite unique within Northwestern Fluids community because I think he's the only one doing astrophysical or geophysical fluid dynamics amongst the fluids. So Daniel did his undergrad at the University of Wisconsin-Madison, then MS at Cambridge, and then he went to Berkeley for his PhD and postdoc at Princeton. He joined Northwestern in 2020, and he's in ESAM as an assistant professor.
Great, thank you. Yeah, so thanks for the introduction. So today I'm going to be telling you about some of my work on convection and waves. And as I'll show, this is motivated by different problems in both astrophysical and geophysical fluid dynamics. But I think that hopefully kind of the concepts will be interesting more broadly. So first I want to start with just convection. So this is a movie of convection. This is a classic fluid dynamics problem. You have a hot plate down here and a cold plate up here, and that heats up the fluid. So the temperature here is being shown in red for hot and blue for cold. So you can see these hot fluid parcels rising, the cold ones falling, and this leads to some large-scale mixing. Okay, so this is a very classic problem. You have kind of solid boundaries on both sides, fixed at constant temperature. Now, if you try to translate something like this to natural settings in geophysics and in astrophysics, it's the kind of like natural settings are actually a little bit different. Whoa, it's really laggy. This is an example of something that might happen in the Earth's atmosphere. So here we have a volcano which is emitting hot fluid. So that's kind of like the hot plate that we had in that previous movie, except instead of being a distributed source, it's a localized source. And as that hot fluid rises up due to convection, you can see that at some point it actually stops moving. Okay? And that's because the top boundary of the atmosphere isn't just like a solid plate kept at low temperature. Instead, you have the stratosphere. Okay, so what's the stratosphere? Well, if you look at the density as a function of height in the atmosphere, the lower part of the atmosphere, that's where we are, is called the troposphere. And in that region, you can think of the density as being about constant with height. So the density isn't changing very much. And the density of the gas being emitted from the volcano is at lower density than the surrounding. So because of that, it's going to be able to rise. You might see that there's some incursions here due to mixing, and there's actually multiple components of gas here that's at different densities. But most of it starts up here in the stratosphere, because in the stratosphere, the density actually decreases with height. So a fluid parcel which starts off at some low density here, it rises until it hits this point where the ambient density matches its own density. These regions here are called stably stratified because you have dense fluid below light fluid. So that's a stable configuration. And basically what I want to do is just zoom into this region up here. So this is my version of that. So we have, again, the density as a function of height, and you have dense fluid below light fluid. Now, when you have fluid motions in the stably stratified region, it's stable, but there are wave-like solutions that you get here. So why does that happen? Well, imagine again that you had this fluid from the volcano, this gas from the volcano, which hits its neutral buoyancy height, as it's rising up through the atmosphere, gets into the stratosphere, which is stably stratified, but doesn't just stop there. It gets displaced. Okay, so okay, well, I guess for the volcano it would be moving upwards, but now let's just assume that that you kind of like push a fluid element downwards. If you compare its density to that of its surroundings, you can see that this fluid element here is denser than its, is lighter than its surroundings. The density is less than that of its surroundings. And because of that, there will be a buoyancy force that will go upwards, okay? So this fluid element is going to accelerate, it's going to start moving up. It'll reach its original position, but then overshoot and not up too high. Now it's going to be denser than its surroundings. The density here is larger than that of its surroundings. Because of that, there's going to be a buoyancy force downwards, and basically this fluid element is going to undergo these vertical oscillations. That's what we call an internal gravity wave. So you get these oscillations here. We can work out that the frequency of the oscillation is related to the strength of gravity, and also to this density gradient here. Okay? And the stable stratification is related to the negative density gradient, so that this whole term is positive, so that you get a real frequency. This combination is known as the buoyancy frequency, or sometimes also called the Brunt-Väisälä frequency, and it tells you the frequency at which you get oscillations for something which is moving vertically. Okay? So the key thing here is that the oscillations are only associated with these vertical motions, or if you're taking like a global perspective, it should be the radial direction. If you're, say, like looking at a sphere at very large scales. So here you have a frequency which is given by the buoyancy frequency, an oscillation frequency. If you're only moving in the horizontal direction, there's no gravitational restoring force. So in that case, the oscillation frequency is 0. And if your motion is at some angle with respect to the vertical axis, called that angle theta, it turns out that, you just kind of smoothly connect the n squared here to the 0 here, get omega is equal to n times cosine of theta. Okay. So this is the dispersion relationship for these waves. So you could write like a wave number, which is perpendicular to the direction of the oscillation, and rewrite this cosine theta as a ratio of wave numbers in different directions. Okay, so there's kind of this general system that occurs, as I mentioned, in the atmosphere. You have convection in one part of your domain of interest, and then you're stably stratified in this other part. And because of that, you get these internal gravity waves up here. And one of the major themes of my research is trying to understand what's going on at this interface between convective and stably stratified regions. And so today I'm going to be talking about the waves that get generated by this convective turbulence. But there's other interesting questions, like where exactly do we expect this interface to be? Because depending on the properties of the convection could maybe move this interface or deform it in interesting ways. There's all sorts of mixing processes which occur at this interface, etc. So I just want to quickly give a couple of examples of where this occurs in nature. I already mentioned the Earth's atmosphere. So you have the troposphere. That's where we are, the lower part of the atmosphere. And if you have a storm, storms are convective events that occur in the troposphere. So here we're plotting temperature fluctuations. So you have warm temperature fluctuations associated with upflows in a storm in the troposphere. And then once you go into the stratosphere, that generates these internal gravity waves, which are kind of these oscillatory motions that you see up here. So that's an example of something that happens in the Earth's atmosphere. And these waves can actually have some interesting dynamical effects. In particular, they're able to drive a large-scale global flows known as the quasi-biennial oscillation. So here, what I'm plotting is like the east-west average wind speed as a function of time and as a function of height in this stably stratified region of the stratosphere of the Earth. And And it undergoes these regular oscillations. So you can see that it starts off in the lower part of the stratosphere. You have wind in the easterly direction, and above that you have wind in the westerly direction. And then this kind of propagates downwards. You have westerly wind over easterly wind, and it just oscillates like that. The oscillation period is about 26 months. So it's almost every 2 years. So that's why it's a quasi-biennial oscillation. And this is extremely regular. It's been measured at least since the 50s, and it's been oscillating regularly this whole time, which to me is kind of remarkable because I mean this is like an extremely high Reynolds number phenomena. Flows in the Earth's atmosphere are a really high Reynolds number. And this is it's 20 to 30 meters per second, and yet it still is able to organize itself in this extremely regular pattern, which has been very regular up until 2016, where there was this disruption. Okay, so you can see there was this blue phase, which was starting to propagate downwards, and then kind of got disrupted, and it switched back to red. Okay. So ever since the 50s, it's been completely regular up until 2016, and we don't understand why it's so regular, and also why maybe occasionally it's not regular. So it's thought that these oscillations here are actually being driven by the interaction of these mean flows with waves, with these internal gravity waves, which are generated by convection. So one idea that people have is that maybe due to climate change, the convection, the storms are changes the properties of the waves, which might mean that this type of oscillation we get in the stratosphere might change. Okay, so that's an example in the Earth's atmosphere, and I want to turn to stars. So almost every star has both a convective region and a stably stratified region. For instance, if you look at the sun, the outer 30% of the sun is convective, the inner 70% is stably stratified. If you look at a more massive star, this is a diagram of a star which is 3 times the mass of the sun. It's kind of flipped. You have convection in the core of the star. The star is so luminous. There's so much energy being generated by nuclear reactions in the core of the star that the only way for that energy to get out in this core region is by convection. So you have a convective core, and then the outer part is stably stratified. So here you can have convection generate waves. And what's interesting thing about this is that those waves could make it all the way up to the surface, and you might be able to measure them at the surface. And if you did, that would give you information about something that's going on very deep inside the star. And recently, there have been new observations available that might make this possible. So this is an example of a satellite called TESS, was launched about 4 years ago. And this is a satellite. It's a transiting exoplanet survey satellite. As the name indicates, what the satellite does is that it looks at other stars really carefully, and it hopes that by chance there's a planet orbiting that star that goes between you and the star. If that happens, the planet occludes the star for a short amount of time, which makes the star look a little bit dimmer. So this satellite was put up to try to find planets orbiting other stars. I personally find those a little bit boring because we don't really know anything about them other than that they're there. So I think of this as the fact that maybe the stellar astrophysicists really duped the rest of the astronomy community into putting up a satellite which is really good at studying stars, because it needs to stare really carefully at all these stars and measure the brightness of those stars really precisely. If you do that, you end up with so-called light curve. So this is a measurement of the brightness of a specific star, HG 212581. As far as I know, these numbers are just random. So this is the brightness of the star as a function of time. The data is extremely dense, so it's kind of hard to see exactly what's going on. But what's a little bit easier is if you take the Fourier transform of this, you can see that there are very distinct oscillation frequencies. So this is just the Fourier transform. So we have the amplitude as a function of the frequency, and can see that there's a bunch of oscillation modes. Okay, these are the global oscillation modes of the star, and then if you you could do the inverse problem and try to infer what is the property of, like, what are the global properties of the star which give rise to these oscillation modes. So that's called astroseismology, and in analogy to like geoseismology here on Earth. Now, one kind of surprising feature about these light curves is that for massive stars, those are the ones that have the convective cores and have these stably stratified envelopes where you can get these internal gravity waves. Almost every convective star has a large power in fluctuations at low frequencies. So here I'm showing this is the power in the fluctuations as a function of frequency. You have a lot of power at low frequencies, and it kind of dies off a bit at high frequencies, and you might see individual oscillation modes out here. But these are exactly the frequencies you expect with the internal gravity waves. Okay? So there's a question, is this excess power at low frequencies due to internal gravity waves excited by convection? Okay, so that's kind of the question that I'm going to be building towards in the rest of this talk. So we want to try to understand how does convection excite internal gravity waves? What kind of amplitude of waves would you get? What's the property of waves that you get? Does it match with things that you observe in stars or in the atmosphere? So how do you study this problem? Well, for normal fluids, if you have a normal Boussinesq fluid, you have this inverse relationship between density and temperature, where low temperatures correspond to high densities and vice versa. But it turns out that water is a really weird substance, and the density maximum of water isn't at 0 degrees, but it's actually at 4 degrees. Okay? And we can take advantage of this in order to study waves in convection. What you do is you take a tank of water, cool the bottom to 0 degrees, keep the top at, say, like room temperature. Between 0 and 4 degrees, the density is going to be increasing with height. And because of that, you're unstable to convection, because you're going to have dense fluid above light fluid. Between 4 degrees and, say, room temperature, then the density is going to be decreasing with height, and that means that you're stably stratified. So then you're going to have your internal gravity waves. So you can do a laboratory experiment and get convective excitation of internal gravity waves. So this was done by my colleague Michael Levalls in France. So this is his apparatus. This experiment was actually done at UCLA while he was on sabbatical, and what he did was you just cool the bottom of your tank of water to 0 degrees. You can see there's a bit of ice, and then you can see what's going on inside. So he has this thermistor array. You can move it up and down, so you get the average temperature as a function of height. You can see in the bottom part of the tank, there's this large region where the temperature is about 4 degrees. So this is the convective region. The fluid is well mixes to 4 degrees. Then up here, you're stably stratified. So the temperature is increasing up to room temperature. So you can see in this image, there's this like green laser sheet. So he did PIV measurements to get the velocity profile. Here I'm showing just in the stably stratified region. There's also PIV done in the convective region, but here you can actually see the waves being generated by the waves which are generated by the convection. And for me, what's remarkable about this is the amplitude is really small. So the amplitude of these waves, the velocities are about 10 microns per second. But I guess they're coherent over long enough times that you can measure it with PIV. Okay, so he ran these experiments, but we kind of want to understand more precisely what was going on. So to do that, we wanted to turn to some numerical simulations. So I ran some numerical simulations of this problem using the Daedalus code. So this is a code that I helped to develop. I just want to say a few words about it. These are some of my collaborators on the Daedalus project. I specifically want to point out Keaton Burns, who's at MIT, who wrote most of the code actually while he was a grad student. And then Jeff Vassell here, who's at University of Sydney, who developed many of the algorithms that we use in the code. So these are the equations that we're going to solve in order to model the system. So we're going to do incompressible Booston-esque hydrodynamics. So we have a momentum equation with a buoyancy term. This buoyancy term, we're going to say that the density perturbations are proportional to T minus T naught, which in this case would be 4 degrees squared. Okay. So this is different from the normal Booston-esque approximation where the density perturbations are just given by the temperature perturbations. Here we're taking into account this nonlinear equation of state of water, or approximating as quadratic. Then we just have a normal temperature equation and incompressibility. Okay, so this is in terms of math the equations that we're solving, and then to solve these in the Daedalus code, what you do is that you just type them out as a string. Okay, so if you have a different equation, you just put in just type it out differently. So in this case, we're breaking things down into from this vector notation into different components. So u here would be the horizontal velocity. So we have time derivative of u minus Laplacian of u plus the x derivative of pressure minus u dot grad u is equal to negative u dot grad u. Similar for the vertical velocity equation, where now we have our nonlinear buoyancy term, temperature equation, divergence equation, etc. Okay. So this code is extremely flexible, and I think now we have there's over 140 papers that have used Daedalus to solve all types of different problems, not just in astrophysics, but also in biological fluid dynamics, limnology, plasma physics, a very wide range of subjects. Okay, getting back to the question at hand, wave sharing by convection. This is actual result of the simulation. So what I'm plotting here, so it's a two-dimensional simulation. The tank was kind of quasi two-dimensional, so this is not such a bad approximation. So we have horizontal direction, vertical direction. In the bottom part here, I'm plotting the temperature, and I plotted red to be the cold fluid because that's buoyant. Because I don't know what that is. Some convection or something. Okay, so here red would be the cold fluid, which is what's buoyant because we're below 4 degrees. Okay? So red is the cold buoyant fluid. Blue is the hot dense fluid, which is kind of like falling down. And so I'm plotting the temperature down here, and then in the upper part I'm plotting the vorticity so that you can see the waves that are being generated by the convection. So you have these convective upflows which go near this interface region, and then it generates waves.
Is it periodic box or
it's periodic on the sides. Yeah. I'm using stress-free boundary conditions. It's been 7 years. I don't exactly remember how I did it. I think I actually simulated this twice. So if you flip it like this, then it's actually periodic. Okay. And then I'm showing half the simulation. Although now, in the intervening 7 years, we've modified the code so that you can just simulate it once. Okay, so this is so this is what we get from the simulation. We compared it to the experiment. Many things were very similar. Few things were different because of boundary conditions. But we kind of wanted to get a better physical understanding of this process of wave excitation by convection. So we turned to the literature of thinking about some of the models that people have proposed for how these waves are generated, and say that there were kind of two main mechanisms that were relevant for our case here. So there's this bulk forcing mechanism and interface forcing mechanism. Okay, so the bulk forcing, what that is that you say that within the convection zone there are stresses, and those stresses couple to the evanescent tails of the internal gravity waves. So the waves are propagating in the stably stratified region. They're evanescent in the convective region, but the idea here would be that kind of you're exciting the waves within the convection zone, and they kind of leak out into the stably stratified region where they can then propagate. Okay, so that's the bulk forcing mechanism. The interface forcing mechanism is that you think of the interface between the convective and stably stratified layer as being like the surface of a drum, and then the convective plumes are like mallets that are then deforming that surface, which then generates waves up into the stably stratified region. Okay, so those are the two pictures. So what we did was that okay, yeah. So what we did was that we wanted to run simulations that kind of captured these two ideas and see if those simulations were able to reproduce the full result that we got. So to test the bulk forcing picture, what we did was that we solved the linear wave equation, which is okay. So this is the linear operator associated with the gravity wave, and then okay. And then we're solving this as an inhomogeneous equation where you have a forcing term which is given by Reynolds stresses within the convection zone, and those Reynolds stresses we take from the simulation that I just showed you. Okay, whereas this simulation we're kind of like only trying to solve for the waves. Okay, so that's the first case, and then to test the interface forcing, what we did was again we're solving the same linear wave equation, but now we don't have any volumetric source term. Instead, we're going to force the system using a boundary condition. Okay. So what we do is that we measure an interface from the full simulation, and then see how that interface is moving, and then use the motions of that interface as a boundary condition to force this equation. Okay, so I'm going to show you a movie of the wave fluctuations just in the stably stratified region. So I've cut out the convection below. In our full simulation, so that's including everything. In this simulation where we have this bulk forcing term, this volumetric source term for our linear wave equation, and then these two simulations are forcing it with the bottom boundary condition. In this case, what we did was that we took the bottom boundary to be the 5-degree isotherm, and then in this case we took the 8-degree isotherm. Okay, so what does that mean? Well, remember the convection mixes things up to be 4 degrees. So the convection zone is going to be about 4 degrees. So here 5 is about like 4 plus epsilon. Right? I didn't want to do 4. I was worried that maybe occasionally you'd say that like the interface was like all the way at the bottom or something weird like that. And then the 8 degrees we picked 8 because again we have this quadratic equation of state. So a fluid which starts at 0 degrees actually has the same density as at 8 degrees. Okay, but in practice this 8-degree interface, and it's the same thing as the 5-degree one. It's just like a little bit higher up. Okay, so I'm going to play the movie. And so there's some initial transient that occurs, but first, if you look at the full simulation and the bulk forcing simulation, you can see that there's a pretty good match. Okay, so when I first made this movie, I actually thought that I messed up and was like playing the same thing twice by accident, but Yeah, but it seems like this bulk forcing picture does a really good job of reproducing what's going on in the full simulation. Okay. The correlation between these two velocity fields is like 99%. By contrast, if you look at the full simulation relative to this interface forcing simulation, you can kind of see that it might be a little bit hard to see on the screen, but there's kind of like this high frequency flickering. Okay. So the interface forcing simulation seems to think that there should be kind of this high frequency component that's not really supposed to be there. So we can be a bit more quantitative and plot the wave power as a function of height and frequency, and see that the full simulation and bulk forcing simulation do really well, or maybe I should just say that the bulk forcing simulation matches this very nicely. Whereas the interface forcing simulations, there's kind of this extra power at high frequency, which is not supposed to be here. And so here the darker colors correspond to larger quantities. Okay, so it seems like this bulk forcing picture works well. So we have this physical interpretation that the waves are being generated within the convection zone, and then they kind of leak out. Okay? And this is basically like the Lighthill theory of wave generation. Although Lighthill applied it, of course, to sound, here we're applying it to internal gravity waves, which Lighthill himself actually said you could not apply his theory to internal gravity waves. Okay? So there was a paper submitted to JFM trying to apply his theory to internal gravity waves, and he rejected it. I think maybe he was like editor-in-chief at the time, so he rejected it. He said, "You can't apply my theory to internal gravity waves." I'm not entirely sure why. I've had some people look to see if they can find the correspondence, but we haven't really found it yet. But despite what he thought, the theory seems to work really nicely. Okay. So again, the idea here is that we say that the waves in this stably stratified region, they're given by there's this Reynolds stress source term, and then in order to see how many of them leak out into the stably stratified region, you need to convolve with the Green's function. So the Green's function is easy. That's just from linear theory. The question then is what's the source term? Okay, so what's the Reynolds stresses that you get in the convection zone? And so that's what I'm going to talk about next. Okay, so we want to come up with some simple theory to like a simple heuristic theory to make estimates of what the Reynolds stresses would be like in the convection zone, and then we're going to convolve that with the Green's function, and then predict what waves, what's the spectrum of waves that you expect. Okay? And by spectrum of waves, what I mean is that I want to know what's the power, or like what's the energy in waves that have different frequencies and different wave numbers. Okay? So the way that we're going to do this is that we're going to imagine that you have some convection, you have some turbulence, okay? And the turbulence we're going to decompose into eddies. We're going to calculate which waves are being excited by a single eddy, and then we're going to sum up all the eddies. This is obviously a pretty bad description of turbulence, but at least it gives you something, and then we can try to compare that to what we get in simulation. Okay, so the idea here is that you imagine you have an eddy of a certain size and a certain coherent time. So we're going to say that the eddy is coherent for its turnover time, and then we want to calculate what are the waves that are going to be efficiently excited by this eddy. Okay, so first let's think about the spatial structure of the wave. Imagine you have a wave whose wavelength is much smaller than the size of the eddy. Well, when you integrate the wave fluctuations over the eddy is going to be some large scale feature. You're integrating something that's oscillatory. That's actually going to be you're going to get something which is exponentially small. Okay, so for large wave numbers, actually you're not going to get very much excitation by an eddy of this size. Whereas if you're looking at small wave numbers, so a large scale wave, if you might be able to fit in multiple eddies within that wave, and you might get lucky, and the eddies might line up with each other such that you get a coherent excitation. Okay? Now, of course, this isn't going to happen all the time, but in this case, you only get like a square root of n sort of suppression, opposed to here you get an exponential suppression. Okay? So these eddies are going to be much more effective at exciting low wave number rather than high wave number waves relative to their own size. So that's good. And then you can make the same argument for temporal variations, which would say that you're going to excite things which are at long waves that have long periods relative to the coherence time of the eddy. Okay. Then you can do a calculation with the Green's function, make various heuristic limits, and calculate what's the wave energy flux that would be excited by this eddy as a function of both the size, so here this h over tau. So this is the size over the turnover, the coherence time or turnover time. So this here is just the velocity to the third power. And it also depends on the properties of the waves, the frequency, the wave number, and also the buoyancy frequency. Okay, so this is kind of what you would get for a single eddy, and basically this formula is only valid in these two limits. Okay, so in these cases you can't use it. Okay, so now we're going to add up all the eddies. So the idea is that we're going to assume that you have a largest scale where you have a large length scale h, so that's going to be the size of the convection zone. Then you have a convective time c, which is kind of the turnover time in the convection zone. And then you're going to have your Kolmogorov cascade, where you're going to have smaller eddies, which rotate faster. And then you could ask, well, which waves are being excited by each of these? Again, you only excite things at low wave numbers and at low frequencies. Okay, so this eddy can only excite in this region here. Then this eddy will excite in this region, etc. Okay. So okay, now there's only one piece of the puzzle left, which is the fact that you have a radius damping of these waves. The radius damping, the strength of the damping goes like the wave number, the perpendicular. By perpendicular here, I mean perpendicular to gravity. So it's like the horizontal wave number to the third power. And so that's saying that if you have a very small scale wave, then it's going to damp more easily. Okay, so that kind of makes sense. But what's maybe a little bit less intuitive is that high frequencies also damp quickly. Okay? So, excuse me, low frequencies damp quickly. So normally, if you think about sound waves, for instance, it's high frequencies which damp quickly. Here, low frequencies damp quickly. That's because a low frequency wave has a very small vertical wave number. So the vertical and horizontal wave numbers are linked by the dispersion relationship. So if you pick a certain horizontal wave number and you go to low frequencies, that corresponds to a very small vertical wave number. Okay, so so what this means is that you're going to damp out waves that are at high frequencies, at high wave numbers and low frequencies. So once you take into account the effect of damping, you're only going to be able to see like the waves up here. So the physical picture that we have is that if you're interested in this wave here, this high frequency wave, that we think that this wave is not going to be excited by this big eddy, large scale eddy, which carries most of the energy, because the frequency decoupling is just wrong. Okay? The only way you can get this wave is by having this really small guy up here producing this wave. Okay? And because of that, the high frequencies are going to be excited much less than low frequencies. But high frequencies are damped less. So it's kind of like a trade-off. If you go through all the math, you end up with this prediction here, which is that the wave energy flux scales like the frequency to the minus 13/2 power. Okay, so a very, very steep frequency dependence. It's going to be very, very weak excitation at high frequencies. And then it also has this wave number dependence, goes like wave number to the 4th power. Okay, so let's try comparing this to simulations. So this is a simulation run by Louis Cousson in France. So it's a 3D version of the one that I showed you earlier. So here you have a convection down here, and you have waves up here. You have a convective plume rising up. It generates Reynolds stresses near the surface, which creates a cone of waves. Okay, if you take a cone and you do a vertical slice, as shown here, you can see these kind of tilted lines of constant phase. But you can also take horizontal slices, which is what I've done here. So here we're in the bottom boundary layer of the convection zone, middle of the convection zone, and top boundary layer of the convection zone. If you're in the stably stratified region, now that cone, you take a slice through, it makes these concentric circles. Okay. So Louis ran these simulations, and then he measured the properties of the waves. And so here, for a couple different simulations, applying the wave energy flux as a function of frequency, and you can see that indeed it's falling with frequency, and like here the frequency is only changing by 1 order of magnitude, but it's going from 10 to the 5 to 10 to the -1. The blue curve is this minus 13/2 power law. Okay, so it seems to match pretty well in both of these simulations. And then you can also look at the wave number dependence, and that also seems to match up that we get this wave number to the 4th dependence as predicted. It's given by the blue line. Okay, so the theory, I mean, it seems a little bit scuffed. I don't think anyone believes that you can think of turbulence as just being like little eddies that you can treat independently, but somehow it seems to give something which matches the simulations pretty well. Okay. So with all this, then you could ask yourself, well, okay, can we use this to try to make a prediction of what you might see at the surface of the star? Try to compare that to the observations. Okay, now I just showed you this Boussinesque Cartesian geometry simulation, and there's lots of differences between that and what's going on in a star, and in particular, something that's very important is that these stars are in spherical geometry. Okay, so to address this, and of course many other problems, we decided to try to kind of extend our Daedalus code so that we could also do spherical geometry. And I don't have too much time to talk about that, but I just want to mention one of the things that's a little bit tricky about this. What we wanted to do is to, again, be able to solve arbitrary PDEs that you could enter in as a string in spherical geometry. The issue is when you have to deal with vectors, okay, or tensors more generally. And the reason is that the coordinates, the coordinate unit vectors are spatially dependent in spherical geometry. So here what I'm doing is imagine you're at the equator of the sphere, and you want to represent a vector which is just pointed upwards. Okay, it's uniform and going upwards. Okay, so that's our vector here. You can see that there it's in the phi hat. It's in the e phi direction. Now, if you're on the left side, you can see that your unit vectors change. So if we have our uniform, so this is like the most boring vector field imaginable, it's just a constant. This one is actually in the negative e phi direction. So what that tells you is that this vector field, it seems perfectly benign. It's just constant in Cartesian geometry. But in spherical geometry, you see that it's actually discontinuous, because on the right side of the origin, it's given by e phi, but then on the left, it's given by negative e phi. So what we've done is that we figured out spectrally accurate, so exponentially converging basis set, which automatically has all the proper discontinuities for any function that you might want to represent. Okay? And if you do that, then you can do these calculations very accurately. So as an example, so here I'm looking at the equator of some sphere. So I have some velocity field. If you look at the x and y components, everything looks fine. But then if you look at the r and phi components, you have this discontinuity, and it's completely captured by the basis functions that we use. Okay, so with all this, you can actually run a simulation. So here I'm going to show this simulation. This is a simulation run by Evan Anders, who's a postdoc in Sierra. So that's the Astrophysics Center here on campus. So he's a Sierra postdoc fellow that I've been working with since I got here. And this is a model of a star which is 40 times the mass of the sun. So it has this convective core. And here we're plotting temperature perturbations. So you can see that that in this convective core, there's the convection is being generated by the fact that there's nuclear reactions at the core of the star. Those nuclear reactions generate heat, and then you get this hot fluid which is moving outwards, and by chance it's kind of like aligned. It's kind of like moving towards you a little bit. Okay, so that's the red fluid here. Then it hits this boundary with the stably stratified region and gets deflected. So it gets deflected, moves around like that. You can see that there's like this separation layer right here. So it gets deflected, and then you have a return flow, which is on average a hole. So that's the convection, and then out here you get waves. Okay, so those are our internal gravity waves, and we want to try to measure the characteristics of those waves. So what's the spectrum that we get? So just to remind you, this was our prediction that we had seemed to work well in Cartesian geometry. Okay, so these results are kind of like hot off the press. So the figures maybe aren't super nice, but what we did was we calculated this wave energy flux as a function of frequency. These are different simulations, but they all seem to kind of line up with this solid line, which is a power law. So it's not frequency to minus 13 halves, it's frequency to minus 15 halves. Okay, what does this mean? I mean, the theory was just supposed to be for turbulence. I mean, I wouldn't have thought that anything would be different in spherical geometry. Somehow it seems to be a bit different. So I'm honestly like a little bit concerned. So at this stage, like I don't really know what to make of it, but that's kind of the result that we have so far. And it seems to be really robust. We've done different Reynolds numbers, different resolutions. It seems to be pretty robust. Okay. The wave number spectrum that does seem to match the old frequent wave number to the fourth power. Okay. So it seems to pretty much match the theory. But not exactly, but I don't know. Okay, so this is something that we're trying to understand better right now. But you can just take these results and try to apply them to the stellar case. Okay, so now the issue is that what I've been talking about so far is just how the waves get generated by the convection. I haven't talked about how the waves then would propagate to the surface. Okay. So that's actually a separate calculation, but in some sense it's easier because it's just linear wave propagation. Now, it's not guaranteed that it's linear wave propagation. I mean, in theory, the waves could become nonlinear, but it seems like the linear wave propagation actually works pretty well in this case. The waves that are excited are not at very high amplitudes, in part because of this damping process. Okay, the most efficiently excited waves are at low frequencies, and those frequencies actually get damped very effectively. So the only things that you really see are going to be things that that have like lower power. Okay, but so I don't have time to get into the linear wave propagation, but it's a kind of fun problem that you can do. but you can do it and then make a prediction of what you would see at the surface. Okay. So then, so this is kind of like the final result. So what I applied here is the brightness fluctuations that are actually observed for some star. Okay. And this star is inferred to have similar properties as the star that we're simulating, so about 40 times the mass of the sun. And then we can look at what comes out of our simulations, and this is this is the curve that we get from our simulations, where we take our wave flux that we measure from the simulations and then propagate that to the surface and ask what do you see at the surface. And for instance, here you can see there's these peaks. Those are the standing modes. Okay. Which I mean, so you don't see any standing modes in these observations, but I showed at the beginning of the talk how you get these standing oscillation modes sometimes. Okay, so that's in our prediction. But I would say that the overall characteristics of these two curves are very different. In particular, I mean, they actually seem to match up well at like the very low frequencies. Get fluctuations about 10 to the minus 3. But then if you're looking at fluctuations at a frequency of like 1 day, what's observed is like, again, 10 to the minus 3, whereas our simulations, it would only be something like 10 to the minus 7. Okay, so I mean, that's like 4 orders of magnitude smaller. It's like a big discrepancy. So in the end, it's kind of like bad news. We think that actually these fluctuations we're seeing at the surface probably can't tell you about what's going on in the convection in the core of the star. At least not for this star. Okay? You might ask, well, what's producing these fluctuations then? Well, it turns out that these stars, they have like a very tenuous little convection zone at the surface that people often forget about. And we think that might actually be polluting what's going on here. Okay? So hiding all these waves. And interestingly enough, there are certain stars where we predict that there should not be any convection zone at the surface. Now the regions of the surface are actually unstable to convection, but interestingly enough, the Rayleigh number is below the critical Rayleigh number. Okay? I never thought that there'd be any situation in nature where you would have a Rayleigh number below the critical Rayleigh number, but the thermal diffusivities are so high that that can happen. Okay? So we do think that there are a range of stars where you don't have these surface convection zones, so you might have a chance of being able to see this signature. Okay, well, so I'll just put up my summary slides, my summary right here, just to quickly say the main points. It seems like these internal gravity waves are being excited by Reynolds stresses in the convection zone. We can predict the spectrum of the waves using a very heuristic model of turbulence. It seems to work like okay in spherical simulations, although there's still question marks here. And it's unclear how this exactly relates to stellar observations, but I think it's more useful to have an idea of what to expect than just kind of flying blind. So thanks for your attention.
Yeah, questions? Yeah.
I have a quick question because, as someone who has no clue about turbulence, do you have an intuition, some explanation why the energy spectrum is kind of, as a function of the wave number, is kind of like, it looks like it has an inverse cascade?
Yeah.
Yeah. You can show, yeah, that one.
Yeah. Okay. So this is not the spectrum of the turbulence. This is the spectrum of the waves.
Yeah. So
yeah.
What kind of is there any intuitive explanation why it goes this way?
Yeah. So this goes back to my picture here. So at a fixed frequency, you see that all these waves here are being excited by the same eddy. Okay, but this eddy here is at a given wave number, and it's not going to be able to couple very well to this really small wave number. It's going to couple much better to this intermediate wave number, and then once you get larger than that, then it's not going to work very well at all. So So the idea is basically like that you don't get much excitation of waves here because you have to have this large wave being excited by little eddies. Here you're getting a small wave excited by little eddies. That's better. And then here you have like a really small wave trying to be excited by a little eddy, and that's very inefficient. So that falls off.
Okay, I'll talk to you when we are talking. So
I
I guess we
think
have to get out.
the next thing is, yeah, we have to get out, unfortunately. So let's thank our
Thank
speakers.
you.